In this recording, we're going to talk about the estimation of caloric expenditure from indirect calorimetry and the calculation we use to do this. Caloric expenditure is calories per minute. Okay. And calories are units of heat. Okay. And the whole purpose of measuring calories is to determine how much work an individual is doing. Now, we can measure calories directly with a process called direct calorimetry. What we do is we measure the heat coming off of an individual, and because heat production is directly related to energy expenditure, which is the same thing as ATP production, okay, the higher the calories per minute, that means that we are using more ATP, an indication that we're doing more work. So calories give us an indication of how much work you're performing or how much work you performed. Direct calorimetry, measuring heat directly coming off the body, is possible, but it requires a large chamber, it's fairly expensive, it's fairly bulky, and it doesn't capture rapid changes in caloric expenditure. There is a way that we can actually estimate heat production by measuring VO2. VO2 stands for oxygen uptake, oxygen use, oxygen consumption. Multiple terms for the same thing. Basically, how much oxygen are you using? Okay. And as you can see in this formula, which represents oxidative ATP production, okay, going back to chapter 2, going into the metabolic pathways, we have glucose that goes into glycolysis, we have FFA that goes into beta oxidation, and we have oxygen that goes into the electron transport chain. And as a result of oxidative ATP production, we produce some ATP, we produce some CO2, some water, and one of the other byproducts is heat. We produce heat. So yes, we could actually measure heat coming off of the body, and we would be able to quantify it in calories per minute, and it would give us an indication of how hard somebody's working. But there's an easier way to do this, which is pretty accurate. So yes, there is a direct relationship between energy expenditure and heat production, but energy expenditure and heat production are also directly related to oxygen use. Okay? That's what this is, oxygen use, VO2. Okay? If we produce more ATP, it's because we're putting in more oxygen. Okay? So the only way to get more ATP from oxidative ATP production is to put in more oxygen. Okay? And it's easy to measure oxygen consumption. Okay? All we need to do is put a mouthpiece on an individual. I showed you this in class. It's figure 5.2 in your book. We put a mouthpiece on an individual. We determine how much oxygen they're inspiring. We subtract the amount of oxygen they're expiring. And the difference is going to be the amount of oxygen that they used. Okay? And the more oxygen they're using indicates that they're making more aerobic ATP. Okay? And at the same time, they're producing more heat. So what we're going to do here is I'm going to show you the process of taking data from indirect calorimetry, okay, taking VO2 numbers, VO2 data, and using VO2 to estimate caloric expenditure. Okay, so we are going to estimate caloric expenditure which is kcals per minute, which is heat production. We're going to estimate it from VO2. So we're going to take some VO2 data and we're going to convert it into caloric expenditure. So let's go through this step by step. There's going to be a few things you need to know, and it's a very basic process. So first of all, the first thing you need to know in order to convert VO2 into caloric expenditures, you need to know the actual VO2. You're going to also need to know the VCO2, which I'll explain in a minute. So VO2 is oxygen use. VCO2 is CO2 production. Okay? Because we don't use CO2, we produce it. And we don't produce oxygen, we use it. So VO2 is oxygen use. VCO2 is CO2 production. And we can measure these numbers using indirect calorimetry. Okay? And we usually express these values in liters per minute. Okay? So this is the indirect calorimetry. Okay, this is figure 5.2 in your book. And you can see that we have an individual exercising and he's wearing a mouthpiece. So we're capturing all of the air going in and we're capturing all the air going out. Okay. And the exhaled air is going to go into some gas analyzers. And we're going to know exactly how much oxygen he's using and how much CO2 he's producing. Okay. So remember, VO2, oxygen use, can be calculated as how much oxygen goes in minus how much oxygen goes out is going to give us how much oxygen actually got used. And then VCO2 is the reverse. Okay? We can measure how much CO2 he's exhaling, and we subtract how much CO2 he took in, and that's going to tell us how much CO2 he produced. Okay, so this is a production, this is a use. So we're measuring what's coming in, we're measuring what's coming out. Okay, and by knowing what's coming in and what's coming out, we can very easily, through subtraction, calculate VO2 and VCO2. Okay, so we do that through indirect calorimetry. Okay, so first step is to measure VO2, VCO2. We do that with the indirect calorimetry. Normally you would do this in the lab. In class, I'm just going to give you these numbers, and we're going to do an example in a minute. The next thing you need to know is the caloric equivalent. Okay, caloric equivalent is for every liter of oxygen used, how many calories are being burned. Okay, and caloric equivalent is really easy to figure out because it's a constant. Okay, and so all you need to do is have a table with the constants, and you can look it up on a table. However, in order to look up a constant on the table, you need to know the RER, okay? Because the caloric equivalent is not the same all of the time. Okay? Caloric equivalent is a constant that varies with the food being oxidized. So if you want to know what an individual's caloric equivalent is at a moment in time, before we can determine their caloric equivalent, we need to know, well, how much of their oxidation is coming from carbohydrate, how much of their oxidation is coming from fat. If 100% of their oxidation, 100% of their aerobic ATP was from carbohydrate, then we would know to use 5.05 as our caloric equivalent. If 100% of their ATP was coming from fat oxidation, we would know to use the caloric equivalent of 4.69 because these are constants. Okay? But in reality, remember, nothing is ever 100%. Nothing's ever 0%. So the real caloric equivalent is somewhere in between these two numbers. Okay? So in order to be able to figure out their caloric equivalent, we need to know what fuels they're using. We need to know the contributions of oxygen and fat to oxidation. And we've already talked about this in class. This is where we use RER. Okay, so you need to know RER in order to use the table in order to determine the caloric equivalent, the correct constant. And we've talked about in class how to calculate RER. It's a very simple calculation. It's VCO2 over VO2. And when you do this, you're either going to have VO2 and VCO2 already because you measured it in the lab or because I gave it to you. Okay? So before you can use the table, you need to calculate RER. Once you calculate RER, you use the table, you look up the constant, and now you have your caloric expenditure, your VO2, your VCO2, and you go to the last step, which is to calculate caloric expenditure. So this just shows you the table. Once you know somebody's RER, you can look up the correct caloric equivalent. And the numbers that I gave you, if RER was 0.7, it's assumed that they're using 100% fat, this would be the caloric equivalent. Okay? If they were using 100% carbohydrate, the RER would be 1, and this would be the caloric equivalent. But the reality is we're in here somewhere. Okay? And in order to determine which of these caloric equivalents to use, you calculate RER. Okay, so you need to know how to calculate RER. It's VCO2 over VO2. It's going to give you an RER. You're going to look at the table. Let's say your RER was 0.85. Then you would look at the table and you would know that the caloric equivalent is 4.86 calories per liter of oxygen consumed. Okay, so that's how you use the table. All right, so we're on our last step, which is to calculate caloric expenditure. Okay, so here's some real data. Let's go through these steps. Okay, so the first thing is go to the lab, measure your VO2 and VCO2. Okay, so I've already done that. And I've told you that the individual was using 2.07 liters of oxygen per minute and producing 1.87 liters of CO2 per minute. Okay. Step 2, calculate RER. Okay. So to calculate RER, you need to know the formula. This is something you're going to need to memorize. Okay. It's VCO2 over VO2, okay, which is, in this case, 1.87 divided by 2.07. And if you do the math here, you will get an RER of 0.90. Okay, so you want to round your RER to 2 decimal places, 2 numbers to the right of the decimal point. Now that you have your RER, the next step is to identify the caloric equivalent. Okay, and for this you're going to use the table. Right? So we determine that the RER is 0.9, therefore the caloric equivalent is 4.92. Okay, what this means is this individual is producing or is burning 4.92 calories for every liter of oxygen they consume. Okay. Now that you have the caloric equivalent, you can do the last step, which is to actually calculate caloric expenditure. All right, let's look at what we've done so far. So step 1 was to measure the gases. Okay, I gave you those numbers. I measured them in the laboratory. I gave them to you. Okay, the VO2 was 2.07 liters of oxygen per minute. It could also be written as liters of oxygen per minute. Same thing. Here we don't have to specify VO2 because the VO2 is here, but it's the same thing. We also measured VCO2, and we got 1.87 liters of CO2 per minute. Okay, so this was oxygen use, this was CO2 production. Step 2 was to calculate RER so that we can use the table. And RER is VCO2 over VO2. Okay, so in our case, that's 1.87 over 2.07, which gives us an RER of 0.9. Step 3 is to use the table to determine the caloric equivalent. So if you look at the table and we looked up 0.90 and we found that the caloric equivalent for 0.90 was 4.92 kcals per liter of oxygen consumed. Okay. Then the last step is to calculate caloric expenditure. Okay. Caloric expenditure is calories per minute. Okay. You're not there yet, right? We have calories per liter of oxygen. We need calories per minute. Okay. So all you do is very simple. You take the VO2, Okay. You multiply it by the caloric equivalent, okay. The liters of oxygen consumed are going to cancel. 4.92 times 2.07 gives you 10.2, okay, and the units are calories per minute. Okay, that was our goal, was to calculate caloric expenditure, and now we've done it. So the question was, here's his VO2. How many calories is he burning? He's burning 10.2 calories per minute. Okay. So it's very simple. I will give you these numbers, okay, and these had to come from indirect calorimetry from the laboratory. And then you need to know what to do next. Okay, you need to determine the caloric equivalent, and that comes from a table. But before you can use the table, you need to determine RER. So you need to calculate RER, so you should know how to do that. Then you use the table to determine the caloric equivalent. Then all you do is multiply the caloric equivalent times VO2. And if you write out your units, it's going to make sense, right? Because if you plug in VCO2 here, it won't make sense, because this is liters of VCO2 per minute. Okay? And liters of VCO2 per minute wouldn't cancel with liters of VO2 per minute. So just looking at the caloric equivalent, you know that you need to multiply it by VO2, not VCO2. Okay? So VO2, liters of VO2 cancels, you're left with calories per minute. And so the answer to the question is 10.2 calories per minute. Okay? And we got that number from indirect calorimetry. Okay. So we measured gases with indirect calorimetry. We calculated RER. We used RER to determine the caloric equivalent, and then we calculated calories per minute. Okay, so in summary, we used indirect calorimetry to estimate caloric expenditure. Which is calories per minute. And it's a pretty accurate measure at rest and during low to moderate intensity exercise. We haven't talked yet about what steady state is, but steady state exercise, because with rest and low to moderate exercise, most of your ATP production is aerobic. Or oxidative. And so this here is a really good representation of what's going on. Okay? We're putting in some glucose and fat. We're putting in some oxygen. We're producing ATP, CO2, water, and heat. Okay? And remember, the whole purpose of this is to figure out how much work are you doing, how much heat are you, how much ATP are you using. We can't actually measure ATP, but we can measure heat production. But that's big and bulky and not very feasible. But because all of the things in this equation here are happening together, okay? If one thing here increases, they all increase, okay? So if most of your ATP is aerobic, then all of these things are going to increase together. So as you're using more ATP, you're producing more heat, you're also using more oxygen. Okay? And that's what allows us to estimate heat production from oxygen use. Okay? And oxygen use can be measured with indirect calorimetry. Okay? Along the way, we also need to know VCO2 because we need to calculate RER. And we're not going to talk about this right now.